Hey there, my name is Alejandro, and welcome back for day 83 of me doing the NeetCode 150 challenge. So today we're doing another LeetCode medium grass problem, and without further ado, let's get straight into it. Okay, today we get a LeetCode medium problem 417, Pacific Atlantic water flow. Oh boy, this is a long one. Okay, there is an n by n rectangular island that borders both the Pacific Ocean and the Atlantic Ocean. The Pacific Ocean touches the island's left and top edges, and the Atlantic Ocean touches the island's right and bottom edges. Oh, the grid itself is the island. Okay. Borders the Pacific Ocean and Atlantic Ocean. Pacific Ocean touches the left and top, so like the left wall and top wall. Okay, and the Atlantic Ocean touches the right and bottom edges. Okay. Okay. The island is partitioned into... So is there one island? Oh, okay. The island is partitioned into a grid of square cells. Okay, yeah, it's a grid. You're given an n by n integer matrix heights where heights of RC represents the height above the sea level of the cell at coordinate RC. So I'm guessing if it's height 0, then it's water. The island receives a lot of rain, and the rain water can flow to neighboring cells directly north, south, east, and west. Okay, so like left, up, right, or down. If the neighboring cell's height is less than or equal to the current cell's height. Okay, so you can go to an... So essentially you have up to 4 neighbors, but you can only really go to neighbors if the neighbor's cell is less than or equal to the current... Okay, sure. So essentially it's like, you know, it's a way of defining neighbors. Okay. Water can flow from any cell adjacent to an ocean into the ocean. Okay. Return a 2D list of grid coordinates result, where result of I is equal to Ri of Ci, denotes the rain that can flow from cell result of I denotes that rainwater can flow from... Okay, so essentially every single coordinate that has water that can flow interesting. Okay, so essentially every single, so output is going to be a bunch of coordinates to both the Pacific and Atlantic Oceans. Okay. Oh, and so the oceans are essentially like outside the grid, but essentially all of these guys, so this can reach the Pacific Ocean and this can reach the Atlantic Ocean, right? So essentially you do this in kind of a DP way, right? Or like essentially you memoize, or okay, so essentially it's like, okay, the corners are immediately obvious, right? Because it says, okay, this is okay. It's kind of a long problem, but I don't think it's this all that difficult. Yeah, rainwater can flow to neighboring cells. Yeah. Water can flow from any cell adjacent to an ocean into the ocean. Okay. So the very first thing we're gonna do is m comma n is equal to the length of heights and length of heights of 0. Okay, so essentially def, here we'll do def can flow into Pacific Ocean. Self, an I and a J, right? And here we'll do, first of all, self.m, self.n equals m, n. Self.heights is equal to heights, if anything. So here we'll have another function, first of all, def inbounds self until like an I and a J. Here return, 0 less than or equal to I less than self.m and 0 less than or equal to j less than self.n, right? And here we'll just do assert self.inbounds of I, j. Okay, so now essentially, okay, so if you're one of these squares, then essentially you can immediately go. So this is, okay, so essentially if your row index is 0 or your column index is 0, it's good. So return I equals 0 or j equals 0, right? Otherwise, def can flow, we'll just do this, can flow Pacific. Or if I equals, then we'll do return true. Then we'll have to do, okay, really we should cache these results. Okay, before we do the other one. So this is essentially a base case. And then it's like, each node has potentially up to 4 neighbors, i.e. left slash down slash right slash up. Here we'll do, self.directions is equal to, we'll do 0, 1, 0, -1, 1, 0, as well as -1, 0. There we go. But can only go to adjacent ones. Can only go to adjacent ones that have west. Okay, so west of the neighboring cell's height. So the neighbor to adjacent neighbors whose height is less or equal to current height. Okay, so here we'll say for dx comma dy in self.directions, neighbor x, neighbor y is equal to I plus dx. Here we'll just call this di dj, I plus delta I. Here we'll just call it neighbor I, neighbor j, and j plus dj. And here we'll say if height is equal to self.heights at index I, index j. If, this is constant time, so if, so the point is essentially it's like, you know, you'll do it for a certain ij. Essentially, you'll see if, okay, can any of your neighbors reach the Pacific Ocean, right? And then same thing for the Atlantic Ocean. And the point is like, you know, for every single ij, they're dependent on like, you know, the adjacent ones. You essentially have base cases where it's like, you know, if you're on these borders, then it's true. And then it's like you just cache results. So it's like, you know, if you computed like essentially it's going to be a lot of repeated work. And so you can just cache results to kind of avoid that, right? Kind of like a DP type of approach. Height is equal to self.heights of ij. If here we'll do self.ifs, first of all, self.inbounds, well here, okay, self.inbounds, neighbor I, neighbor j, and something popping, okay. What was I, oh yeah, height is if it's not in balance, then continue. Here we'll do neighbor height is equal something popping, it's just weird. Neighbor height is equal to self.heights at neighbor I and neighbor j. Here we'll say if neighbor height is less or equal to height, then we can traverse to it, right? And then we'll say if self.can flow Pacific, that neighbor, neighbor j, then we return true. Right? Otherwise, if this is not the case for any neighbor, then we just return false, right? So the point is like, essentially it's like, okay, if you're like this 5, essentially you want to be able to reach the Pacific Ocean by, essentially by either going to this square and then going to the Pacific Ocean, or going to this square and then going to the Pacific Ocean, or going to this square and then going to the Pacific Ocean, or going to this square and then going to the Pacific Ocean, right? The point is that we add caching so that essentially we don't do like, repeated work. So that's nice and handy dandy. Now the only problem is if I do this guy, right, and this guy looks at this guy, then actually, yeah, we can't really do caching in this way, right? This is not a directed acyclic graph. So we can't really do an approach like this, right? So if anything, we can do like a DP, but we gotta do bottom up. Or like, yeah, like, okay, the point is like we essentially gotta do these ones. Then we gotta do these ones. Then we got to do these ones. Then we got to do these ones, and then we got to do these ones, right? And for Atlantic Ocean, it'll be the opposite way. Do these ones, these ones, these ones, these ones, and then this one. Oh, man. Or would you ever want to go right? What's an example? Like, would you ever want to go right or down? Is kind of my question actually. Because if I only, let's do something interesting here. Left, comma, self dot, or left, comma, down, comma, right, or right, comma, down, comma, left, comma, up is equal to, here we'll do, to go right, 0, comma, 1, go down, is 1, comma 0. To go left is 0, comma negative 1. To go up is negative 1, comma 0. Self dot right, self dot down equals these directions. Self dot right, self dot down, self dot left, self dot up equals self dot directions. There we go. Or if anything, we'll just do that. There we go. Something's clicking, it's bothering me. Okay, yeah, so certain bounds, yeah. So what if we just do, I just don't know if this will work, right? So if we'll do self dot left and self dot up, right? Okay, it's just it's an important criteria, right? So like, what if like, no, right? Because like, what if like, this was a 20 and this was a 20? But that's like you could go here, here, here. Yeah, this is not going to cut it, right? Okay. Yeah, it's not going to cut it to just look left and right. But yeah, honestly, otherwise, but it does make sense to essentially do this in this order, right? These cases are trivial, right? These are all true. And for each of these, we'll say whether it's true or not, right? So essentially it's like, there's a topological order to this thing, right? Like it's like bottom up DP. It's like you gotta specify this ordering, right? You just have to be careful about it. right? You can't memorize in this way and like go left, right, up, down, and go crazy, right? Because it's like if you go right and then back to left and right and back to left, right and back to left and so on, it's like they need each other to essentially compute the result, and it'll never get anywhere, right? So okay, you can't do things in this way. Okay, if anything, let me just restart the problem. Let's just restart the problem. We'll do m comma n is equal to the length of heights of 0. Directions. Here we'll do, again, the right, down, left, up is equal to 0, 1, 1, 0. Okay. 0, -1, and -1, 0 is equal to right, down, left, up. Okay. Okay, so populate all the cells that can reach the Pacific Ocean. Right? We need to do it where it's like, first, we know all the cells where I equals 0 or j equals 0 will yield true. Then we want to do all the cells where I equals 1 or j equals 1. And I equals 2. Is it, no, it's m by n. 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yeah, so in this case, it's conveniently in that way, right? Or no, or am I stupid? Because now at this point, it's essentially claiming that you can only go left or up, right? This is interesting. Because if I do all of these, and yeah, I know they're true, then it's like, I can't just do all of this here, right? Because like, what if something like this guy, or like, yeah, what if, well, say this guy is stuck, right? It can't go to this 3, okay, it can technically go to this 2, but if this was a 3, right? And this is a 1 and 2, it can go to the right and go here, right? That's the problem. You can't go right or down, and it might be necessary in order to solve the problem, right? You can't assume you're always going to go left up. If I do it in this way, I'm assuming it's going left up. So this idea is not going to work. Okay, this is an interesting problem. And okay, no, I've never solved this problem before. Okay, so this is a brand new problem. And the constraints, well, m and n are 200, so this is very, very brute forceable. Okay. Interesting. Okay, so we finally have a challenging problem on our hands. So how do we do it, right? So the problem is that, like, if I look at a cell like this, I want to be like, okay, can this guy or this guy or this guy or this guy reach it, right? But if I look at something like this guy, I'd be like, okay, can this guy or this guy or this guy or this guy reach it? So the point is like 5 needs 3 and 3 needs 5. So how do I get rid of that dependency, right? How do I turn this into like a directed acyclic graph? Or like, you know, like for like, you know, you can only do dynamic programming whenever you have a DAG. So how do you remove the need for the dependency? So you have to think of it as flow. Do I have enough juice? Oh, no. I was going to say, okay. I was about to say, like, oh, wait, you can only go if it's, like, you know, greater than or equal to. If it was, like, you know, it must be greater than, then it would be very easy, right? Because then it's always the case that, like, you can either go through one and not the other. But if you have something like 2 and 2 here, that's infinite, right? Okay. I was about to realize that this problem would, for a moment I thought this was going to be really trivial. But no, they make it, it can be less than or equal and you can still traverse. So if it was just less than, then yeah, obviously it becomes very, very trivial, and I can just do what I did before. Whereas like, yeah, you can look at the neighbors, and then you don't have to worry about the infinite money glitch, let's call it, because it's like, if they're both equal, then you can't go to either one, or otherwise, if like, if a neighbor is less than you, then going back will not be possible, right? And so, but in the case that they're equal now, you can essentially infinitely ping pong. So okay, I thought I was about to be clever, but no, the same issue still persists for when the sea level is all the same. So maybe it's like, when things are equal, I solve the problem for it there and then, kind of a thing. Okay, sorry, it's like click-clacking, and it's just, okay. I'll try to ignore that. Blah, 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 blah. Pacific Ocean and Atlantic Ocean. First of all, yeah, bottom left and top right are guaranteed Gucci. Because, yeah, those both border Atlantic Pacific Ocean. Okay. How do you remove this dependency, right? You need to go to a square. Essentially, you need to find a path. How do you remove the? So yeah, so you can't. I mean, if anything, we can do like a BFS from every single cell, right? I guess we could do that. That's very inefficient, but I guess the constraints are pretty small. So we could definitely do a BFS from every single cell. Is that the expected solution? So, okay, m times n is 200. 200 squared. So this is like 2 times 10 squared. So squared. Oh yeah, that'll work. Oh, is that literally the solution? Just BFS from everything? Okay. Just I wanna. Just it feels like a bummer, right? It's just like something about this. Okay. You know what? We can just try the brute force solution for now. So it'll just be in this spirit, like for I in range m, for j in range n. Do a BFS traversal. You've reach Pacific, reach Atlantic is equal to false, comma false. Here we'll do first of all, Q is equal to a collections dot deck. I'll have I comma j. Well, length of Q is greater than 0. If reach Pacific and reach Atlantic, and here we'll say res.add I comma j and break this while loop. Okay. Otherwise, here we'll just do x comma y is equal to q dot pop left. And here we'll do visited is equal to set, and it adds in I comma j. Okay, the click clack. Okay, queues equal to collections on a deck. Here we'll do. At the very end of things, we'll just return res, right? If anything, we can do list of res. X comma y is equal to q dot pop left. If x equals 0 or y equals 0, reach specific equals true. If x equals m minus 1 or y equals n minus 1, reach Atlantic is equal to true. If both of them are ever true at some point, res that and then break out of the while loop, right? Otherwise, we'll look at the neighbors. For dx comma dy in directions, we'll say neighbor x, neighbor y is equal to x plus dx, y plus dy. If, here we'll do lambda inbounds, or inbounds, inbounds is equal to lambda some y, 0 less than or equal to x less than m, and 0 less than or equal to y less than n. Okay. If it's inbounds, neighbor x, neighbor y, here we'll do this, and neighbor x, comma neighbor y, not in visited, and we need the heights of neighbor x, neighbor y, less than or equal to, height is equal to heights of I, j. Height, then we can consider it. Visited.add, neighbor x, comma neighbor y, q that append neighbor x, comma neighbor y. Right, so what about something like this? So here, oh gosh. Interesting. Two, three, four. Wait, why? Oh, it can't reach both. Wait, what? No, this is fine. It's if both are true. Why is this doing this? If you're on the border, then this is true. If you're on that border, then this is true. Right? It has to be this way. Oh, this needs to be XY. Okay, there we go. So that's an expected solution. Is it fast enough though? Okay, it is. Although, okay. Clearly, my solution is a little bit slow though. Okay. So we take 2700 ms, which is accepted. Is this a, yeah, this is a LeetCode medium. This is not a LeetCode easy. Okay. Okay, people are doing this in 10 ms, 32 ms, and so on. Okay. So clearly, I have a working solution, just not a optimized one at all. Okay. So there must be some way to do this much more efficiently. Okay, so right now, by the way, in case you're watching the video right here, what I did quite simply is literally like, for every single position ij inside the grid, literally just do a BFS reversal to see if I can reach both the Pacific and the Atlantic Ocean, right? So essentially for every single square, like let's say there's 5, I'll literally just expand as much as I can. And at any point, if I reach a node on this border, I'll be like, oh, I can reach the Pacific Ocean. And at any point, if I reach a node on this border, I'm like, oh, I can reach the Atlantic Ocean. And if at any point I realize I can reach both, I'm like, okay, cool, let's have a solution break. Otherwise, like, I expand everything that node could look at. And if it happened to be hashtag no bueno, then it happened to be hashtag no bueno, right? Okay, so yeah, so the point is essentially like, BFS every single square that you can see from every single, like for every single square in here, do a BFS reversal to see every other reachable square, and check if like, you were able to reach a square that's in this border as well as this border, and that means you can reach both oceans, right? And only include those as part of your solution, and there you go, bada bing, bada boom. So now, there must be a way to do things more efficiently, right? Like kind of like a DP DAG. But clearly I can't. Okay, jeez. Okay. So there must be a way to do this efficiently. Okay. See, this is what I appreciate when the input size is small, but it's large enough so it's like it's not that everybody gets 0 ms and there you go, right? Where it's like, okay, here I clearly am doing something giga inefficient, and there's clearly an efficient way to solve this problem. So let's think. What can I do? So yeah, I can't have these guys neighbor because they're just gonna ping pong between them. Or in this case, it's like 5 and 4. There's no problem, right? Because it's like you can go this way, but you can't go this way. The problem is when things are equal. So how do we solve the case when things are equal? Is the question. Yeah. How do we, like I can't just be like, okay, like from like a 2 find like all like reachable 2s and be like, okay, then from then on let's like expand one level, and then for each it's like expand it. So it's just, yeah, that just starts getting a bit too complicated, because for each of these, those look at like ones that are the same and so on. It just starts to get a bit weird. So how do we do this better? So okay, let's look at what's special about these guys, right? So I'm guessing these are, so top and bottom left are obviously part of the solution. So the solution seems to be weirdly the diagonal. Is there any hint about that? Should we be doing this problem inside of a diagonal kind of way? Oh yeah, so this is not highlighted because it can't reach the Atlantic Ocean. So this has enough juice that I can go there and so on, yeah. So maybe it's like I start at the bottom left, and I expand from there, right? Where it's like instead of this and so on, it's like this I know can solve it, right? Who can reach me from here? I can take it. No place I'd rather be. No place I'd rather be. Yeah. So like this 6, okay, this 6 obviously is in the Pacific Ocean and it couldn't go to this 5, which was touching this one, right? But then for something like this, it's less obvious, right? Where it's like it can't really reach that 5. And it had to go to this 4, which is also a possible solution, which can go to this 3 and so on. Is there a way to like, maybe it's like you like, maybe like flip the problem upside down? It's like you then ask yourself, okay, like, you know, from these borders, like what nodes I can reach or something like that? So like from this 5, it's like, no, but then you can't reach this 6. Or, no, you can, because you're going the, if you're inverting the problem, you're going to go the opposite way, right? Where it's like, yeah, you can go to numbers only that are greater than or equal to you. I guess you could do it like that. Where it's like you BFS from the borders. So it's like, you know, you do n plus m df. Oh wait, that's actually kind of cheeky. Wait, if you BFS from every single node on this border, or maybe do we just do these? Do the corners suffice? No, this 4 has nothing to do with this 5. This 4 can reach the Atlantic Ocean and can go there. But we could just do the borders, right? So like here, like, you know, there's M, N, and N. So here I'm doing M times N total BFS calls. If I invert the problem, let's say, I only have to do N plus N BFS calls. So that's an improvement. Although I don't know if that's the expected solution, right? I mean, we can definitely try it, right? Okay, yeah, maybe it does help to think about the problem in that way, right? Where it's like, you know, instead of asking yourself like, you know, can it reach the Pacific and Atlantic Ocean, be like, okay, from these tiles, right, which tiles can be reached? Ooh, if anything, I can do it all in kind of like, yeah, it might be the same work, but I could do a BFS, but instead of starting from one node, right? Yeah, I think it'll be the same overall runtime complexity. It's just, it might be like a little bit cooler in terms of efficiency, or like, you know, a bit sexier. Where it's like I can initialize a queue with all of these guys, and it's essentially, it's like, okay, populate, right? And there you go. Okay, so maybe we can do something like that. Maybe we can do something like that, eh? All right. Here we can even write a function, be like, do def find or BFS. Here we'll take a self and we'll take a queue. Deck, queue, as well as a visit set. Visited is equal to set of queue. Right, and the point is essentially here we can just return visited. Lol. Pacific queue is equal to range M to Pacific queue dot append I and 0. And here we'll do for j in range N Pacific queue dot append I comma or 0 comma j, right? Well, is equal to self.bfs from the Pacific queue can reach Pacific, or Pacific reachable, and then we'll do the same thing. But here we'll do n minus 1, and here we'll do n minus 1. And here we'll do Atlantic. Atlantic, 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 Atlantic. There we go. And then here, like, can I do something like, oh, that was from before. Here, oh yeah, by the way, I learned a new trick that you can do default dict with like lambda, right? So if I do lambda 4 here, right? And I say d is equal to this, and I do d of 12, essentially it'll have the value 4 and so on. So I didn't realize like what we're doing when I do default dict of int, it like passes in the int function which implicitly defaults to 0 and so on. So like I didn't know that, right? It's the point is that you pass in a function, so like the more you know. And so now I can really abuse default dict in the future. That'll be a cool trick. But yeah, but that was what I was doing earlier, I think. But here what I want to do is s1 comma s2 is equal to a set of 1, 2, 3 and a set of 3, 4, 5, and here I want to do s1 dot difference. Is that a function? It is. S2. Yeah, so you can do, or s1 dot, is it intersection? Ah. Hey, there we go. There we go. So here we can do return Pacific reachable dot intersection with Atlantic reachable. And we might have to return this as a list. There we go. Or here we can just test something. Let's just do this. Return set of this. Yeah, so we have to convert it to a list. Not a worry in the world. Okay, so now we can just focus on our BFS, which like this. It's like, okay. So now we definitely need self.heights is equal to heights, and self.directions. Directions. Here, if anything, we can put the BFS function inside of here. Right, so here we'll say we'll do while length of queue is greater than 0. We essentially want every single node reachable from these nodes at the beginning, right? So that's what I mean by it's like, you know, we won't have to do a separate visit set. So this will actually be very, very, very nice and efficient. So here we'll say x comma y is equal to q dot pop left. Here we'll say for dx comma dy in directions, if neighbor x, neighbor y is equal to x plus dx, y plus dy. Here we'll say if it is the case that, you know, the neighbor is in bounds. Here we can probably take the code from down over here, right? Let's grab this. And here we'll say height is equal to self.heights of x and y. So yeah, now we do this. So if it's in bounds, that neighbor, and that neighbor has not been visited yet, and it's actually reachable from our current x, y, then we'll say, okay, cool. We'll mark it visited dot add. Oh, but in this case, we're inverting the problem, right? So inverting the problem. Okay. Visited dot add neighbor x, neighbor y. here q dot append neighbor x and neighbor y. Okay, so yeah, we have the height for dx dy directions, neighbor x, neighbor y is equal to x plus dx, y plus dy, if in bounds, neighbor x, neighbor y. Yeah, the point is essentially we want to populate everything that we can see. So does something like this work, essentially, is my question. No. Well, it would be because maybe there's no self anymore, eh? There we go. Well, my guy. Oh, now it doesn't take in a self. And this is not necessary. Okay, okay. Okay, so that is accepted. Okay, let's get rid of the stuff in here. Okay. Class solution. Okay, submit. Okay. We might not. Okay, we've made the runtime way faster. Oh my gosh, the end is even 1729. I had 2600. Now we're way faster. Okay, that's a lot better. I'm glad to see that. I am very, very, very glad to see that. Okay. Here, if anything, we can just do this and this. And here we'll just do q to add that. There we go. I think maybe that's a bit more concise. Actually, enumerate is gonna fail. Yeah, we just have to convert it to a list. It is what it is. It is what it is. Yeah, we can definitely just, you know. There we go. I like the lambda function. It's fine. Okay, yeah. And this is, you know, this is better than like, you know, because one thing I was realizing is like, you know, for the borders, essentially it's like, you know, I could do the thing where it's like I BFS from this guy, BFS from this guy, BFS from this guy, and this guy, and all the way over here, right? And technically that's better than my original solution, right? Where from the original solution, I BFS from every single square. So at worst, you know, n times n runtime for every single one of the n times m cells, so n times m, all of that squared, right? So n squared times m squared, which is a terrible solution. Then it's like I could do like, okay, BFS from every single one on the edges, right? Which would be 2n plus 2m, all that times n times m, right? So it essentially would be O of n plus m, O of if I write it down, O of essentially n plus m times n times m, right? So essentially each BFS call will be n times m work in the worst case, and then I would be doing this for n plus m total iterations, right? So initial solution went from, it used to be, this is a multiply, this is how we do it, and then instead of doing like, you know, for each one do a BFS, it's like, okay, essentially I want from these guys, essentially show me what is reachable and so on. So instead of having like, a new visited set for every single one and so on, I might as well just add a queue involving all of these elements and then be like, okay, show me everything that I can traverse up to this point, right? And so that's kind of what I did, right? That way it's like you can take advantage of already visited neighbors and so on, including like, for the border ones, like, you don't have to check the border ones and so on. So just to make that bit a little bit more efficient, right? In terms of big O, it's the same thing, right? It'll still be O of n plus m times n times n, where it's like, well, actually no. At the end of the day, now it'll be O of n times m, right? Because essentially I do n plus m, and then I do one BFS call, which is n times m work, right? Then I do n plus m cells put into a queue, and then I do one BFS traversal, that's O of n times m work. So I set up two queues, each of which take n plus m time. Then I do a BFS from those queues, which will take at worst case n times m time. So it's like, in total, I'll have done n times m work. And then I return the intersection of those two, which like, you can just look at its sets, right? So it's like, just like from one set, like only include the ones that are in the set too as well and so on. So that takes linear time. Converting it all into a list takes linear time, and like, there's that worst case, all the elements is n times n, so it takes n times n time. So okay, it's actually O of n times m now. So we went from an O of n times m times n times n solution to I figured out a way to do it this way, but before I wrote the code for this way, I also figured out how to just do it this way, right? Well, the way to do it this way is essentially just BFS from every single one of these guys on the border, but it's like if you just put them all into a queue at the very beginning, then you actually can skip doing this many BFS calls, right? You can just do 2 total BFS calls, right? So actually that is kind of smart. That's very smart on my end. Very smart. And yeah, the point is that we invert the problem. That was also a way. Okay, that was actually a kind of a neat little trick here, right? Instead of thinking of like, from a cell how to get to the Pacific and Atlantic Ocean, just be like, okay, from the Atlantic Ocean, what can I reach? And from the Pacific Ocean, what can I reach? And what crisscrosses, right? So that was a kind of a nice realization there as well. Okay, so we can submit this again. Okay, nice. We're in the standard deviation curve. That's exactly what we'd like to see. We beat 55.53%. We're above the average. There we go. Bada bing, bada boom. Yeah, maybe I could optimize it a little bit more, but I'm definitely more content with that solution than the very first one where we took a little bit more time than 35 ms. But okay, and yeah, this recording is like a little less than an hour long. So it's finally like one of the NeetCode 150 problems. It challenged me a little bit. So that's always nice to see. But okay. As always, in all my videos, I do a quick recap of as I was able to solve the problem. So for this one, okay, so where do I even begin? The very thing that I was just talking about right now is essentially, okay, I first solved this problem in a very trivial way, right? Where right now I have a 35 ms runtime solution, but at the very beginning I had about 2700 ms. And so the way that I wrote 2700 ms is essentially I brute force, right? So the point is essentially it's like you want to know the number of squares that are essentially valid. A square is valid if it can reach both the Pacific Ocean and the Atlantic Ocean. So what does that mean? Essentially, all of these squares here, right, that are on the left or top border can reach the Pacific Ocean by definition. All these squares here that are on the bottom or right edges can reach the Atlantic Ocean by definition, right? And then it's like, okay, you're able to go to a neighbor if and only if the neighbor, so these values represent heights, you can only go to a neighbor if the neighbor has a height that is less than or equal to you. For example, from this 5, you can go to this 3 because 3 is less than or equal to 5, right? But from this 3, you can't go to this 5 because it is not the case that 5 is less than or equal to 3, right? So you can go to neighbors that are less than you or equal to you in height, right? So the point is like, yeah. So I think that in this it was like, seawater and so on. So it's like, from a hill, it's like, water can only like go straight, or it's like, it can go down. Like, think of it like Minecraft, right? It's like water can't pass through like, a dirt block that is one tall or a million tall, doesn't really matter, but it can definitely go straight or it can go downwards, right? So that is kind of the idea there, right? Now, the way that I solve this in the very inefficient way, which is the n times m times n times m, so n squared times m squared, very inefficient 2700 ms solution, is what I did is essentially it's like, okay, let's group through every single cell, and for every single cell, let's run a breadth first search to essentially find out all of the reachable cells, right? And when you do that, keep track of any cells that you see that are either on this border or on this border, right? So every time you essentially initialize two variables, like, can I reach the Pacific and can I reach the Atlantic Ocean to false for both of them. For every single cell, do a BFS from that cell, essentially expand to every single cell that you can go. So like from this 5, it's like, yeah, I can go to this 4, 3, 1, and 3, and then explore from there and so on. So essentially do a BFS to traverse every single position that you can reach. And so for each cell, you have up to 4 neighbors. But for example, this 3 doesn't have this 5 as a neighbor because it's not the less than or equal case. So it's actually that's how you traverse. You'll be kind of limited. And essentially, through your traversal, every time you traverse a node, you ask yourself, okay, is it on the border? And if it is on this border or this border, then okay, set my can reach Pacific Ocean Boolean to true. And same thing, if it's on this border or this border, then set my Atlantic Ocean Boolean is equal to true. And essentially, keep going through your BFS, right, until either you exhaust every single node, or at some point you essentially say, oh, there was a case where I could reach the Pacific Ocean, and there was a case where I could reach the Atlantic Ocean. This means that the cell ij that I started from can reach both the Pacific Ocean and the Atlantic Ocean. I'll append it to my result, right? So essentially for every single cell, do a BFS from that cell to every other reachable neighbor, and keep track of if you ever reach a neighbor on this edge, this edge, this edge, and this edge. And if you have one that landed on this edge or this edge, plus one that landed on this edge or this edge, then okay, it could reach the Pacific and Atlantic Ocean, so I'll consider that in my result. Otherwise, if you exhausted the whole breadth for search from a specific cell, and you were not able to reach both the Pacific and Atlantic Ocean, obviously you don't add it to your result, right? And then at the very end, you just return your result. So the solution there is brute force. It does get accepted. It is 2700 NMS for me when I coded it up, but obviously very slow, but easy to understand, right? For every cell, just BFS, and see if you can reach both the Pacific and Atlantic Ocean. Very, very straightforward. Now, one thing I realized and asked myself is okay, I had a bit of trouble. Was okay, for a node like 5, right? Essentially, I just want to ask myself, okay, if I want to know if this guy can reach the Pacific Ocean, I can just ask myself, can any of my neighbors that I can reach the Pacific Ocean, right? So it's okay, from 5, it's I can go to this 3, ask myself, can 3 reach the Pacific Ocean? If so, return true. Otherwise, it's okay, keep going. Otherwise, can this one reach the Pacific Ocean? Or this one, right? And the only problem is that you might ping pong infinitely, right? For example, 5's neighbor is 3, right? And 3's neighbor is, 5 is not one of 3's neighbor actually, because 5 is not less than or equal to 3. But the problem is that when you check heights, it's based on less than or equal, not just less than, right? So for example, if you look at this 2 and 2 here, right? This 2, you'll ask yourself, can I reach the Pacific Ocean? So one of the neighbors that I look at is this one, because this one has a height that is less than or equal to 2, right? And then for this one, okay, let's suppose we were not at the border here. Okay, I can't really do that here, but let's pretend that this wasn't on the border of the Pacific Ocean. There was more and so on. From this 2, it's we're gonna ask ourselves okay, one of the neighbors that I can reach to is this 2 over here, right? So it's oh, let's see if this guy can reach the Pacific Ocean. And then this guy, I'm going to ask myself, can I reach the Pacific Ocean? And this guy, I'm going to ask myself, can I reach the Pacific Ocean? And I'm just going to ping pong between these two values indefinitely, because I always check for less than or equal. So whenever 2 cells have equal heights, I might end up just ping ponging between those 2 indefinitely and never ever reaching a solution, right? So that was kind of the thing that I was trying to avoid. If it was just less than, then you could just memorize results and just go about your merry way, right? But since we can't, because it's less than or equal to the heights, we have to think of something a bit more clever. And eventually something that I figured out is okay, instead of thinking as whether a cell can reach the Pacific Ocean and then if it can reach the Atlantic Ocean, let's think of the cells that are obviously can go to the Atlantic Ocean, and from those, take those and essentially be what cells can I reach, but from the opposite way, right? Where it's okay, initially from a cell, you essentially can go to neighbors that are less than or equal, right? Well, if I look at the ones from the Atlantic Ocean, for example, and I say, okay, from these cells, let's do a BFS and essentially populate myself with every other cell that I can essentially reach, but in the backwards direction, right? So for example, this 5 cannot reach this 4. So the point is this 4 wouldn't be able to reach this 5. So when I go in the backwards direction, what I want to check is, does my neighbor have a greater than or equal height to me? That way it's if a neighbor has a greater or equal height to me, that means that neighbor can reach me because I have a less or equal to height to that neighbor, right? So the point is essentially from the Atlantic Ocean, start from this border of all the nodes of all the cells that can reach the Atlantic Ocean, and from those essentially expand onwards to neighbors that have a greater or equal height, because those will essentially that if those have a greater or equal height, then they can reach you, right? So from these nodes that essentially can reach the Atlantic Ocean, essentially expand your search to essentially find nodes that can reach you, right? So it's like, for example, from this one, it's like, okay, I know this one can reach me because 1 is less than or equal to 1, right? For this 5, I cannot say that this 4 can reach me, right? This 4, in order to go to this 5, it would need to be that 5 is less than or equal to 4. Cannot do that, right? So essentially from this 5, I'd be like, okay, it cannot be the case that this 4 can reach me, so I should not include it in my search, right? But definitely, for example, from this one, you can go to this 3 and this 4, right? So what it means in terms of the actual problem is that this 4 can go to this 3 and then go to this 1, right? So the trick was to essentially invert the problem, right? Essentially, start with all the nodes that can reach the Atlantic Ocean, and then from there, expand onwards to essentially nodes that can reach those nodes, right? And then same thing for the Pacific Ocean. And the only difference is that essentially, when I look at neighbors, the only neighbors that are legal to me is essentially those with a greater than or equal value, not a less than or equal value, right? But the way that I do it is essentially like I have a function here called BFS that takes in a queue. So the point is that one way you could do this, by the way, that would be of n plus m times n times n runtime complexity. Essentially, it's like, okay, these are all the nodes that are valid. So essentially, do this node and BFS all the valid reachable nodes, right? So BFS essentially with the other heuristic, right? Where it's like, I can only go to nodes that are greater or equal to me in value because those nodes then in turn could go to me in terms of the actual problem, right? And then it's like, okay, I could do a BFS from this node and a BFS from this node and 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 this node, and then coalesce all those results together and be like, that is all the nodes that essentially are valid in terms of reaching the Atlantic Ocean, right? And then you could just mirror the process for the Pacific Ocean, right? Now, the only problem is that, like, okay, how many cells are there in total? How many BFS calls will we do in total? Well, just for the Atlantic Ocean, the number of valid cells, if m is the number of rows and n is the number of columns, it will be for each of these cells and each of these cells. Here there's m cells, here there's n cells. So it would be n plus m total BFS calls, right? And then for Pacific Ocean, again, m plus n total BFS calls. So in total, you'll have n plus m times n times m work, right? Each BFS call, at worst, you visit every other cell. And so if you do n plus m BFS calls, it'll be n plus m times n times m, right? However, if you start off a queue, right, whereas instead of like, start with just this node and expand, start with just this node and expand, how about, all these nodes, first of all, are valid. So add them all to your initial BFS queue, and from those be like, okay, what are all the essential cells that I can reach, right? And reach in the other specific direction, right? Only consider nodes that could have reached you in terms of the original problem, blah, blah, blah. But essentially, I add these all to a queue and be like, okay, let's BFS to essentially find all the valid nodes, right? And so essentially, it's like, I have these all in my queue, right? As if though I had traversed them in BFS, right? It's essentially, you can think of it as like, you BFS and like from this guy, it's like, you can reach this guy, 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 and you put it all into the queue, and then you like continue the problem from then on, right? So you could have thought of it that way, right? But that way, essentially, I save in a bunch of work, where it's like, okay, now since I started this all in my queue, worst case, I'll end up visiting every single cell in the grid once, which is overall n times work, right? But for the entire Atlantic Ocean problem, I essentially put these all into a queue, ran a BFS, which is at most n times n work, and there we go. So it was just n times n work, not n plus m times n times n work, right? I only did one BFS call. And I do the same thing for the Pacific Ocean. I only do one BFS call, right? So essentially, I have this BFS function, which takes in a queue, because for the Pacific Ocean, it'll be these nodes over here, or these cells over here. For the Atlantic Ocean, it'll be these cells over here, right? So the point is I'll take a cell, right? So it's like, Pacific queue, Atlantic queue is initially empty. For I in range m into the Pacific queue, add, coordinates I and 0, as well as I and n minus 1, right? Or as well as for j in range n, Pacific queue is 0j, right? So essentially, every single position in the grid where it's like, the column is 0, so that means like, this guy, or where the row is 0, which means these guys over here, right? And then same thing for Atlantic Ocean, right? Where n minus 1 is fixed, so it's like, only these guys, or where n minus 1 is fixed, so it means just these guys, right? So that's the point. Then otherwise, it's like, once I have the queue, then it's just standard BFS, right? What we want is essentially the set of nodes that we can essentially reach, right? But the point is that we do the backwards direction, right? We check for neighbors that have a greater or equal to height to us, because that means those neighbors can essentially come to us, right? Where it's like, from this 5, essentially it's like I can't go to this 3 essentially, because it's like, this 3 couldn't have gone into the 5 in the original problem, right? So it's like we're inverting the problem, right? So instead of thinking of cells that can reach the Atlantic Ocean, we're thinking of like, what cells can the Atlantic Ocean itself reach, right? Where it's like, it's just going in the opposite direction. So hopefully at least that part makes sense. And yeah, and the point is essentially just regular BFS, right? It's just like, okay, you have put them all into a set. We essentially want, the set of all the reachable nodes here. And so it's just like, okay, just keep exhausting the queue while length of the queue is greater than 0. Just like, x comma y is equal to q dot pop left, grab the height of that value, and it's like, okay, look for every single valid neighbor, right? So for each dx, dy in directions, right, just like compute the new neighbor x and y coordinates, and it's just like, okay, if that neighbor is inbounds and it's not been visited yet, and that neighbor has a height that is greater or equal to my current height, which means that in the original problem I could have reached myself, then I want to consider it as a valid solution node, right? So here I'll add it to my visit set and obviously add it to my queue so I can keep expanding nodes from that guy's neighbors and that guy's neighbors and that guy's neighbors, right? And at the very end of the day, what do I return? I return the visited set, right? Because I want to know all the nodes I ended up visiting throughout my entire BFS call, right? Because each of those nodes essentially can reach the Atlantic Ocean because I went from the Atlantic Ocean to all the cells I could reach. So essentially these cells now are cells that can reach the Atlantic Ocean one way or another, right? And so I want to return them as a set, right? So that way, essentially what I do is I do BFS and I do it with these cells for the Atlantic Ocean. I do it with these cells for the Pacific Ocean. And so once I do that, essentially it's like, okay, the reachable nodes for the Pacific are essentially BFS with the Pacific queue. The reachable nodes with the Atlantic is essentially BFS with the Atlantic queue. And then what do? We have essentially we now have the set of nodes, a set, by the way, a hash set, but a hash set of the set of nodes that essentially can reach the Pacific, as well as a set of nodes that can reach the Atlantic. Well, we want the set of nodes that can reach both, right? So here's just like, just do hash set stuff. Take the intersection between Atlantic and Pacific, right? So essentially all the positions that are both inside of Pacific and Atlantic, because that represents positions that can reach both the Pacific Ocean and the Atlantic Ocean. And then, obviously this will return to you a new set. So you just convert it into a list, and there you go at the end, bada bing, bada boom, you have every single position that can reach both the Pacific Ocean and the Atlantic Ocean. So the main trick for this was essentially realizing that you could invert this problem, which instead of thinking of cells that can go to the Atlantic Ocean or the Pacific Ocean, think of what cells the Atlantic Ocean can reach, right? In terms of the other way around, right? Instead of from a cell going to neighboring cells that are less or equal in height until you reach an ocean, go from the ocean and explore cells that are greater or equal to you in height, and so that essentially you can mark those as can reach my ocean, right? Do it for both the Pacific and the Atlantic, and then intersect the nodes that can reach either ocean to find out the ones that can reach both oceans, and there you have it. You have a working solution, ladies and gentlemen. And what's nice is that, initially I had a 2700 ms solution, which was of n squared times m squared. If you did it with a BFS, where it's you do the same idea, but BFS from this, BFS from this, and this, and this, you end up having an n plus m times n times m solution. But by just doing it this way, where you only do 2 BFS calls by intelligently adding into the queue all the nodes inside one of the either ocean's borders, you can just reduce the entire runtime complexity to just n times m, and that's how you get this 35 ms running solution instead of a 2700 ms solution, which feels absolutely fantastic. And yeah, so as always, let's make sure that we cross off the fact that we did this problem. So there we go, caching feels absolutely excellent. And yeah, so hopefully that solution made sense. But otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So till then, ciao, ciao, my friend. Bye-bye.